How are you? So on Tuesday we did exothermic and endothermic reactions. Now I'm going to go through these questions, but this last part D, I'm not going to go through because I think, no, I don't think, I know. It's actually more to do with rate of reaction, which is the next thing we're going to do. Okay, so even when I'm marking these, and I haven't marked them all yet, but when I'm marking your homework, I'm only going to go up to part C. Okay, I'm not even going to look at D, because I'm going to get you to do it again, essentially. So obviously, if it's done right, you're grand. You need to redo it. But anyway, okay, I have the homework done here. So the image shows single-use cold packs, which are often used to treat swelling due to a sports injury. A cold pack contains two chemicals which, when mixed, as per the instructions on the pack, result in a drop in temperature at the surface of the pack. Is this an example of an endothermic or an exothermic reaction? So if there's a drop in temperature, that's endothermic. And what laboratory instrument could you use to verify this? You would use a thermometer. Okay, actually that gets so cold you definitely wouldn't even need a thermometer, but if you wanted to actually measure it, you would need a thermometer. So the diagram below shows an energy profile diagram for the reaction that occurs when two chemicals in a cold pack are mixed. On the diagram, show using an arrow the activation energy for this reaction. So the activation energy goes from down here where the reactants are, and then it needs to take in all of this energy in order to reach that minimum amount of energy required for the reaction to happen. So the activation energy goes from down here where the reactants start right up to the top. And what does the shape of the graph tell you about the relative amounts of energy of the reactants and products? So the reaction takes in energy. It's an endothermic reaction which takes in energy from surroundings. So the products have more energy than the reactants. And you can see that here. The products are up here, the reactants are down here. Okay? A chemical uses an energy profile diagram. A chemist uses an energy profile diagram to show the energy changes that take place when a chemical reaction happens. Figure 1 and Figure 2 below show the energy profile diagrams for two types of chemical reactions. So we have the reactants down here and the products up here. You have your activation energy going for the reactants right up to the top of this hill here. And then your overall change in energy. So overall, the energy of the products is higher than the energy of the reactants. And this one here, so the reactants start higher, and over the course of this reaction, they lose energy. The activation energy here is a bit of a kick up, but overall, as I said, the products are lower than the reactants. Okay, so if you compare those to the ones that I have in the notes, they're very similar. So the first one is endothermic. And two reasons I know: the energy of the products is bigger. Sorry now, you should all know what that means, but just in case. Where do I have this? Here. So the energy of the products is bigger than the energy of the reactants, and there's an overall energy gain from surrounding, and that's what happens in endothermic. Okay, it takes in energy, so the surroundings get cold. And then the other one is going to be exothermic, and my reasons are literally the opposite. The energy of the products is smaller or less than the energy of the reactants. So overall, that reaction has given out energy. It has lost energy from the system. So that's the reaction where if you put a thermometer, it's going to get hotter. What is meant by the term activation energy? The minimum energy required to start the chemical reaction is what the activation energy is. Okay, so everything up to there you should have known. All of that was covered the other day. And then, the last bit we will talk about after, we'll probably talk about it after today's class. Okay, so that's the homework. So please make sure that you correct yours. And if you've got incorrect answers, fix them. And if you don't understand why I got the answer I got, you need to let me know. I mean, sometimes it's as simple as I made a mistake. Like, I did a question with my third years the other day and nobody said a word, not a word. And it was only then I happened to go back into it and I realised I'd made a mistake. I'd like added 2 and 4 when I was meant to multiply them or something, and nobody said a word. So like sometimes it's just genuinely that I got it wrong, but you need to be letting me know if for example that first question, if you got exothermic and I got endothermic and you don't know why it's endothermic, you don't understand that, you need to let me know. Okay, so some people are letting me know in when they put up their homework in OneNote. We kind of start a little bit of a conversation in OneNote, or else send me an email. Okay, but anyway, please make sure you're correcting your homework and you're understanding the content. Okay, so this is still chapter 12. Okay, I just sort of split it up into, that's the first part of chapter 12. It's called chemical reactions, and specifically that was exothermic and endothermic reactions. And here it's still called chemical reactions, but specifically here we're going to talk about rates of reaction. Okay, so the junior cycle specification on this one is Chemical World 7, rates of chemical reactions. And what are you supposed to be able to do? Students should be able to investigate the effect of a number of variables on the rate of chemical reactions, including production of common gases and biochemical reactions. Okay, so this is all about the rate of reaction. Okay, and the rate of reaction is the speed in which a reaction takes place. Okay, how quickly the reaction happens or how slowly the reaction happens. Okay, so it's all about the speed. Okay, couple of bits at the start here. I just didn't mention the other day, and they're sort of important. Now, the first one I did mention, the chemicals that react together during a chemical reaction are called the reactants, and the new substance or substances that are formed are called the products. So I did talk about that the other day. I wrote it on one of the diagrams. Yeah, here. Okay, so the reactants are the substances that are mixed together at the start, and the products are when the reactants react, what they make is called the products. Okay, so I just want to kind of have the definition there for you, but we did talk about that. And this is kind of important, and it's a question I've seen been asked. So how would you know? Give 2 ways in which you would know that a chemical reaction has taken place. So I just wanted to list these here, different things. So you might get a change in colour, you might get a change in temperature. So obviously that one there, if it's exo or endothermic, you might get a change in temperature. You might get a production of light. We were talking, was that us? Yeah, it was. We were talking about burning. That was us, wasn't it? So you might get a production of light, an emission of sound. We were saying that when burning occurs, there is a sound. A distinctive smell, you could actually put that with burning as well. And there's plenty of chemical reactions that we do in the lab that end up with a pretty horrendous smell. And bubbles of gas being produced. So the experiments that we're going to do in this chapter, one of the experiments is producing carbon dioxide gas and one of the experiments is producing oxygen gas. So in both cases you're producing gas, and they do gas bubbles. So it bubbles through the liquid and then you're able to catch it. Okay, so they are quite important kind of evidence that a chemical reaction has occurred, okay? And these are some of the bits of evidence. We're going to do an experiment in this chapter where you will see a colour change. Stop thinking now. There it is. Obviously in the last part of it, we're going to do that endothermic, exothermic. So you will see chemical reactions where there's a change in temperature. I'm trying to think of some of the other ones. Definitely the smell. Yes, actually it's the same one as the colour change. Produces a smell. I knew there was one. And then we're going to do the bubbles gas as well, because we're going to produce carbon dioxide and oxygen, not together, separately. Okay? So all substances are made up of particles. Now, this I spoke about as well. Okay? This is connected with what we were speaking about with effective collisions. Okay, all substances are made up of particles. Before a chemical reaction happens, the particles in the reactants must collide with each other. This is called collision theory. Okay, and if we link down here, so we have the more collisions between particles in a given time, the faster the reaction will take place. But not every collision will result in a new product being formed. The colliding particles must have, so this is where you don't just want them to collide. Colliding is not enough. They need to collide effectively. And how do they do that? They do that when they have the minimum amount of energy. And that minimum amount of energy is called the activation energy, which we did talk about the other day. Okay, so we talked about solids and liquids and gases and how they're all made up of particles, and how in liquids and gases the particles can slide past each other, and in gas they can really move. And you mix them together and you'll have particles bouncing off each other. But bouncing off or colliding with each other is not enough. They need to collide off each other with enough energy to react. So it needs to be an effective collision. How do we ensure that we have an effective collision? Because the particles have the activation energy, the minimum energy required to start the reaction. Okay, I kind of liked this. All the energy profile diagrams have that little hump in them, and so the little kick up. So do you remember I was saying the other day that in order to kind of start a reaction, you need to take in energy to kick off the reaction? So that's sort of what's going on here. Oh, you can't see that. That's sort of what's going on there. So they have to take in a certain amount of energy to hit that activation energy, and then the reaction can happen, and you end up with the reactants turning into the products. Okay, you get that little hill in both the exothermic and endothermic. Okay, and it's just that little bit of energy to kickstart the reaction, and then you sort of literally, like this guy pushing this up the hill, he's going to be exhausted to get it to the top of the hill, but once it gets to the top of the hill, let it go. The reaction will happen. Okay, and it's the same with the activation energy. The energy might need to be put in or drawn in. So sometimes the chemicals can do it themselves. They just draw a little bit of heat from surroundings, and that's enough to kickstart the reaction. Sometimes you need to do it, so you might need to heat it up, or we're talking about burning, you might need to strike a match. So there will definitely need to be some input of energy to get up that hill. And once you're up it, then leave the reaction off. Okay, so I just want to briefly talk about rate of reaction, and then we're going to leave it at that. So some reactions are slow and some reactions are fast. The rate of reaction, so I said this up above, the rate of reaction describes how quickly a chemical reaction happens. Okay, so we can control or change the rate of reaction. So in the pharmaceutical industry, they need to be able to do that. So they need reactions to happen particularly quickly or particularly slowly, so that they know how much product they can make and produce. Like all the people that are producing the vaccines at the moment, they would need to be able to say, right, I can produce this much vaccine over the next 8-hour shift. And then obviously they can scale that up to how many people do they have working, over how many hours, so on and so forth. So the rate of reaction can be measured by carrying out investigations, and when we get back to school, we're going to do this, but I'm going to talk through each one. During a chemical reaction, it is possible to measure how much reactant is being used up or how much product is being formed at the same time. Okay, so essentially you have two options. Let me try and highlight this. How much reactant is being used up is the first one, or how much product is being formed is the second one. Okay, so this one here would be how much product is being formed. Okay, so you have the reaction mixture down here. You can see here that a gas is being produced, and then up here they're trapping the gas here, and then they can measure how much there is. And then on the other side, what they're using to measure, so this would be how much reactant is being used up. So what's happening over here, same thing, you have the reaction mixture, you have the gas escaping, and then what you'll notice is that the mass will decrease here. Okay, so that's just two different ways of measuring it. All right, and the question that I didn't end up marking was a rate of reaction graph. Okay, so the slope of the graph can be used to show the rate of reaction. So if it's got a steep slope, it's a quick rate. If it's got a shallow slope, it's got a slow rate. So when we were in maths, it was the exact same thing. So if it was a distance time graph and you had a really big slope, that means that person's going really fast, high speed. Okay, so if you have high slope, you have high rate. Yeah. So a fast reaction will produce lots of product quickly, and this will give a steeper slope. And then so you can see here, right? So the orange one, oh yeah, it says it. The orange one is the faster reaction because it has I should point down here actually, it has the steeper slope. Okay, so that reaction took off much quicker than the red reaction. And then what you notice as well is that up here, the reaction actually ends quicker. So the orange reaction finishes earlier. Okay, so that finished in terms of a time scale, that finished there, whereas the red one continued on and didn't finish till over here. Okay, so you can see that from the start to the spot, nothing else happened on the orange graph. It's completely flat. Okay, it's because all of the products or all of the reactants were used up. So whatever amount of product was going to be produced, it was already produced. Okay, and because it produced it quicker, it finished quicker. Okay, again, if you relate it back to speed, it's like two people going out to run 100 meters. One person runs it quicker. They're just standing there on the line waiting for the other person to finish. It's exactly the same thing. Okay, so there are times when we want the reaction to be quicker, and there are times when we want the reaction to be slower. So it's important that we can control the rate of reaction. Okay, and there's loads of different ways. That's what we're going to talk about on Tuesday. There's loads of different ways to control the rate of reaction. Okay, so I'm not going to go any further. Okay, most of the start of that was a recap of what we did last week. So reactants, products, activation energy, effective collisions, briefly here mentioned how you know a chemical reaction is taking place, which is an important little thing to talk about. And now just an introduction into rate of reaction. So rate of reaction is the speed. We want to be able to control it. We talked briefly here about measuring the rate of reaction. So you can either measure how quickly a product is being produced, or you can measure how much reactant is being used up. Okay, so it's one or the other. So if the reactant is being used up, it's, as in it's going into the reaction and is being changed into something else, and it's not there anymore. So you get this decrease in mass. Or the other way, don't worry about the reactant, just let the reaction happen and collect the product. Okay, so it's one or other. And then if you have a timer beside that, you can time how quickly either the product is produced or the reactant is used up. Okay, a lot of the time when we're looking at rate of reaction, we put it on a graph and it relates directly to what we did in math. And I think you've all done this at this stage. No, you definitely have. Okay, so when we did distance time graphs, if you had a really steep slope, that meant the person was traveling quickly. If you had a less steep slope, that meant the person was traveling more slowly. It's exactly the same thing with chemical reactions. The steeper the slope, the quicker the reaction is taking place. Okay, so we just compared these two. That orange, the beginning of that orange graph is a much steeper slope than the red graph. So the orange reaction is happening more quickly. As a result, because they both start with, I don't know, 50 grams of reactant. So if the orange reaction goes quicker, it means the 50 grams is going to get used up quicker. So the reaction ends a little bit before the slower reaction does. Okay, so what I want you to do for homework, obviously take down your notes as normal. And I'm going to, can I separate these? Oh, I can. So I'm going to make that last question your homework now that you have a little bit more information. Okay, so you've probably already drawn the graph and hopefully you've done that correctly. So it's more about this bit, the conclusions that you draw from the graph. Okay, I'm hoping you might be able to answer that a little bit more effectively now. Okay, so essentially that is now for Monday. Okay, and no, Tuesday, yeah. So that's for Tuesday. We'll have a live lesson on Tuesday and I'll get through a couple of the factors. I don't think I'll get through it all, but I'll get through a couple of the factors that affect rate of reaction on Tuesday. So we'll correct part D and part E. Like I said, I'm assuming you already have the graph done and it's probably done well. I'm just hoping after looking at that other graph and what you've just learned about rate of reaction, you might be able to make a better stab at E. Okay? All right. So have a great weekend and I will chat to you on Tuesday.